Want to hit the? Oh, did you want to hit the lights?
Well, I'll do it when. Sorry.
I'd like to thank everybody for coming first off.
That one, because it's hard to.
I know it's busy schedules and you guys all have a lot of things going on in your lives, and I really appreciate you coming here to kind of share this evening with us. My name is Dave Michael. I teach science here at Bluff High School right now. I'm currently teaching chemistry in a general science class. In addition to that, I'm also a faculty member who's kind of responsible for this NASA Lassen National Park, Lassen Volcanic National Park, Astrobiology Intern Program. And that's really what we're here to kind of recognize and talk a little bit about tonight. And so I'm going to try to introduce it to you a little bit. Hopefully you'll understand exactly what this program is a little bit when I'm done. Once I'm done speaking, Ranger Zachary is going to come up and give kind of a little bit of a history as far as the how our students here at Red Bluff are volunteering with the National Park Service and actually getting some credit with that. So you're going to hear a little bit from him. Then Dr. Dave Murray will come up and talk a little bit also about the correlation between Mount Lassen and Mars. So we'll hear a little bit from him. And then we're going to hear from our students. And our students basically have been working extremely hard for the last 9 months now, okay, since the beginning of school, on research up at Lassen National Park. And it's a very unique thing, unique opportunity that they have, and they're going to kind of talk a little bit to you about what they've been doing. And really, the only way I can describe this is it's one of a kind, okay? And what I mean by that is Lassen National Park, Volcanic National Park, and Ames Research Center got together in about 2004, and their goal was to try to form a union between Ames Research Center and the park, okay? Try to come up with a way that together they could better study what the park's about. They worked on that a couple of years, and then Ranger Zachary and some of the education specialists with the Park Service actually reached out to Red Bluff High School and said, we have these great scientists coming up conducting research at our park. Are you interested in having some of your students kind of follow them along and see what they're doing? Of course, as a school, we jumped on that opportunity and we said, sure, yes, we'd love to have our students exposed to that. In 2008, this entire program went to a whole nother level, and that's kind of where we're at now. And now these students are no longer just tagging along with these scientists and with these rangers, but instead they are actually the ones conducting this research. They're going to present to you today some of their findings, some of the things that they came up with while conducting research up at the park. Now, they were only able to do this under the guidance of Ranger Zachary and then all of our scientists' contacts down at NASA Ames. And those groups of people have been tremendously influential in what they've been able to do. But what we see here is a true program that no other school has the opportunity to do. And we're really fortunate to have that here in Red Bluff, mainly because of our proximity to the park, because of the great relationship we've had with the park through the years, and through the hard work of our students and the demonstration of our students and their ability to basically show that they can be responsible and do this stuff. And so we're really fortunate to have this. As you can probably guess and see, we're all, as adults here, extremely proud of what's going on. And hopefully it can continue to go in a positive direction here and out in the light. So, with this being said, I'd like to thank you for coming. And at this time, Ranger Zachary, you can come up and maybe explain a little bit about volunteering with the park.
Thank you, Dave. Well, it's a pleasure to be here, and I sure appreciate all of you being here. It's an honor to be working with such a distinguished group of students. It's been so fun to be with them, and I love getting together and working with students. And this program really kind of sprouted off of, we have a summer intern program for students that are juniors and seniors that started 17 years ago. And so we've had lots of students from Red Bluff High and other high schools that have participated in our summer interpretive intern program. And then the neat thing about these programs, the Astrobiology Intern Program, the Summer Interpretive Intern Program, as these students are signed up as volunteers with the National Park Service. So they get credit hours for the time and the job duties that they perform at Lassen. And so it's a bonus for everyone, where it's a win-win for everyone, that they get to participate in this program, and they get these credit hours with the federal government as National Park volunteers. And if you start looking around at national parks, there's not a lot of national parks that have volunteers that are under the age of 18. So it's a unique opportunity, as Dave Michael said, to have them participate, and let alone in the case of the Astrobiology Intern Program, where they participate in a place-based, service-based education program where they're assisting in research in a national park in a partnership with NASA and the National Park Service. So it's really a unique opportunity. And of course, if I started saying, if I put out a little letter to all the high schools in California, if they have students that are interested, we'd be overwhelmed. In fact, I already get flack from other high schools in the surrounding areas that say, how come our students can't participate in the program? Well, we can only take so many students, and we only have so much time for this program. So Red Bluff High, which is our in close proximity to the park, it's our gateway to the park, we've been building a partnership, as Dave Mike said, over the years in providing opportunities for high school students. And, you know, we get the cream of the crop here, students that then are going to go on to UCLA, other schools, that then are being leaders in our communities and are going to, you know, they're going to remember, hopefully, Lassen Volcanic National Park and the experiences they've had with the National Park Service, and also share and influence others as they become adults into the real world. So it's just a wonderful opportunity, and I personally thoroughly enjoy working with young people. It's stimulating, keeps you young, you know. You got to keep up with them, right? Right, they have to break trail like today, you know, snowshoeing up into the park and doing all the things that we do. And then for them to be collecting data and information that is part of the Mission to Mars project is just incredible. You know, that they can participate in this and contribute in a meaningful way to NASA and to Lassen. You know, that information and that data that is collected is beneficial to the park and its scientific understanding of the natural resources of the park, and then also for what NASA is doing too. So these astrobiology interns, which is the only category of volunteers in the National Park Service. There's no other astrobiology interns in the National Park Service than what we have on programs. So it's a very unique opportunity, and I really appreciate the support of parents and siblings for them being in this program and for your support of this, because that's what it takes. It takes everyone helping and supporting this unique opportunity for these students to be in this program. So again, I'm going to thank you all for coming here tonight and honoring these students and seeing what they've accomplished. In the 2011, they started in the fall of 2011, 2012. Of course, the seniors started a year before that, so we have seniors and juniors. And just like today, it was really gratifying to me to see the seniors sharing techniques in monitoring and collecting data with the juniors. And the juniors are going to be carrying on what we did last year with the seniors. So it was really neat in that perspective. So again, I want to thank you all. Okay. And Dr. Dave, which is an honor to have you here. How come he's always so red? And so because of this great program. Thank you.
Thank you very much. I'd like to try to accomplish a number of things in a short 20 minutes or so. I'm going to give you a little context for astrobiology and why Lassen is such a valuable resource for us. And that is, astrobiology is sort of taking us out of our modern familiar context to understand early origins and evolution of life on the Earth, and actually to see that if life might exist on other planets. And one of the things I hope to accomplish in this talk is that there's a real functional connection between trying to understand the early biosphere on the Earth and how we would go about looking for life on Mars. And then a little comment at the end about the future of life, and that is, the more we understand these types of systems, the more perspective we have about the future, not only on the Earth, but if we were to, establish a human presence elsewhere, we need to have an operating manual about how we would go about acquiring resources on a place like Mars, and a lot of this research actually informs that as well. So astrobiology is sort of understanding the origin and early evolution of life, its distribution beyond the Earth, and its future sort of in a broad context. What this sort of does is gets you thinking really fundamentally about life. I mean, I don't expect us to see humans walking around on another planet, but there are aspects of life, if it's there, that all life forms might share. And the next slide sort of talks a little bit about that, but it mostly talks about our strategy of where to look. Mars has a surface area equal to all the continents on the Earth. That's a lot of real estate. And how do we know where to search on Mars for the best chance of finding evidence of life? And a concept now that has come forward is what we call habitable environments. And that is, what combination of capabilities or attributes would a given environment have that would allow it to be able to support life? For Mars, because it's such a cold, dry place today, we've thought a lot about water. It's a very dry place on the surface today. And so then the question is, if there ever was more water in the surface of Mars at some time in the past, where might it have been the most abundant, where might it have persisted the most? And so having just about the amount of water you need is one key aspect of determining whether an environment is habitable. But you also need energy, okay? On the Earth, we're sort of very lucky that we have all this liquid water sitting around under sunlight, and so we have this nice source of energy for the plants as well as the water that they require. And of course, we need the ingredients, just like we need to fertilize our fields. We need to provide minerals to organisms in order to build their cells and to grow. And of course, the key is that all these three attributes need to be present at the same place at the same time for a sufficient amount of period so that life can establish itself and it can adapt to any changes that might happen. So this is sort of a combination of what is life. It's an energy-utilizing entity that builds complex cells, lots of information like with the DNA, using these nutrients and of course using water as a solvent. And these are certainly attributes that would apply to life, we believe, on Mars, because just like the Earth, Mars would have been a suitable place perhaps to have water at some time in the past. But what I'd like to do is to just start with the Earth, and start with the familiar on the Earth, and then to get to what has been most significant for the Earth's environment since its beginning. The familiar is the oceans, the continents, with of course the green indicating the most productive areas, and that's where you have this combination of water and light energy present at the surface, and of course they get the nutrients from the rocks on the ground. But there's this whole other Earth, which is revealed when you go to do oceanography and you look at the seafloor and see an enormous ridge system that with these ridge provinces that stretch around the Earth constitute 28% of the Earth's surface. If you consider the fact that these are volcanic constructs and that water goes into the seafloor and then comes up along the ridge crest, forming huge hot springs. So this is the largest single physiographic province on the Earth, and it is a very important force that has shaped the surface geography of the Earth as well as the environment. And if you take the long view, if you take the hundreds of billions to billions of years view, our atmosphere, the fact that we have this amount of water on the surface of the Earth, the fact that the climate is the way it is strongly driven by what we call the heat engine of the Earth's interior. And to try to impress upon you how important this interior of the Earth is, this large mass of mantle and core, it constitutes more than 97% of the planet. We're sitting here at the top 3% on the crust, which, by the way, extends down 20 miles beneath our feet. But even with that 20 miles of thick crust, it's less than 3% of the volume of this Earth. And as you may also know, there are radioactive elements down there, uranium, thorium, and potassium-40, and when they decay, they generate heat. And because rock is not a very good conductor, it takes a long time for that heat that's formed by radioactive decay to find its way to the surface. But when it does, it's like that pot of water boiling on your stove. The heat rises, it flows to the surface, the water flows to the surface, moves away, and then goes back down into the pot and continues to roil as it tries to bring that heat from your burner up to the top of the water. The heat from deep within the mantle is brought up to the surface by this convection. And when it arrives at the surface, in certain places in particular, we call those volcanoes. The point is that volcanoes on the Earth are one of the principal mechanisms by which all this heat from this heat engine in the interior of the Earth finds its way to the surface. And so getting rid of the heat is then a very important function. But the point is that this process, this boiling of the pot that moves the plates at the top of the crust of the Earth, is what has created the geography of the Earth with the continents and the ocean basins. It's created the atmosphere, and it helps to maintain that atmosphere. It's this silent force deep within the Earth that really makes the Earth a place that could have supported life as it has for billions of years. And Lassen just happens to be a little window peek into this engine and into all the attributes that this engine has done to maintain that environment and to maintain life directly, as we'll see. So volcanism is just a major force, and it's driven by this radioactive decay. Now, the interesting thing about that is that radioactive elements decay away, right? Which means that there were a lot more of those guys down there 4 billion years ago than there is today. So yes, indeed, the activity of these volcanoes and everything has been slowly declining over the entire history of the Earth, and therefore early in the Earth they were even more important than they are today. But still, with Lassen, we have a window into how that would have operated. And just to give you an idea, this is the Earth 70 million years ago, the late Cretaceous, the end of the age of dinosaurs. There's now South America and North America, and here is Africa and Europe and Asia. And it looks strange, it should, because the Atlantic Ocean is a lot smaller. That spreading center that is the volcanic system in the middle of the Atlantic has yet to spread the Atlantic as wide as we see it today. You see another margin here where there's a lot of heat coming to the surface. This is this volcanic engine that basically drives the surface of the Earth and its plates. All that light blue that you see are flooded continents. There's so much volcanic activity on the Earth 100 to 70 million years ago that the ocean actually got up onto the continents and flooded the interior of the United States. In fact, California doesn't even exist here. California was constructed sometime after, at least coastal California, after the time of this map. So this really different geography is due completely to this heat, trying to get out from the interior of the Earth, and the volcanic process actually has moved the continents around. Go back 500 million years ago to the Cambrian, it looks even less obvious what the geography was. This is actually a fragment of North America here, but we had this huge southern continent called Gondwana. And this is very important for understanding the origins of some of the earliest shelly animals and marine fauna that arose very dramatically during this period of time. So this engine, this volcanic process, has really made a major effect on the geography of the Earth, and it's continuing to happen. And North America is still getting further away from Europe. We're still spreading westward as we speak. But the amazing thing is that if you go back billions of years, the continents themselves were being put together. These represent ages of the central continent of North America as those pieces were constructed and plastered together. So billions of years ago, we didn't even have a North American continent. And so even the continents themselves, because of volcanism, volcanism, their origin. It's really the volcanic process of the interior of the Earth and what that's done to the crust that has created continents as we know them. And so as we go back like 3.5 billion years ago, this is a mural you can see at the Smithsonian in Washington, the Museum of Natural History. It's a different world. I mean, it's a world where volcanic activity was probably twice to 3 times more than what it is today, because you had a lot more of those radioactive elements, a lot more of that heat coming to the surface. Continents that are nice and stable as we think of them today didn't exist. There was land, but it wasn't nearly as stable. It was much more rich in the kind of lava rock like you see if you go to Hawaii or the Columbia Plateau up in Washington and Oregon. And of course, we had a lot of heat coming out, forming the hot springs. We still, of course, had oceans. There's good evidence for that prior to 4 billion years ago. Atmosphere was very different, though. It had a lot more CO2. Guess where that CO2 came from? And it was really then the relevant environment to which we trace life's beginnings. We know that life began prior to 3.5 billion years ago, and therefore it began in an environment dominated by volcanism. So you want to understand the early biosphere and its environment, you've got to understand what volcanism has done in the case of the Earth's earliest history. Now here's the interesting point, is that this idea about having radioactive elements and heat inside the planet and heat coming to the surface and doing stuff like this, this is a general property of planets. It doesn't just have to be the Earth. It could be Mars, it could be Venus, it could be Mercury. This is the beginning of a concept of how we could take our lessons from the Earth and translate this to other worlds and get a little bit of an idea of what the early environments were like, how they might have changed through time, and how they might have been or might not have been habitable. So this is an insight from understanding the early evolution of Earth that can be translated to Mars and to other planets. In this context, we have geologic evidence. This is like a big time clock for the origin of the Earth at 4.5 billion years ago. Sort of winds around on the clock face up to the present. And I'm sort of shown on here the various evidences we have for early life. Life, we know, goes back at least 3.7 billion years ago, so that's getting back towards the origin of the Earth there. And it was single-celled organisms, all the way up until we get very late in time to the first shelly invertebrates in the Cambrian. As I mentioned, actually, there's a few things just before that. And all the wonderful plants and animals that we know of really are just represented in this last little slice of Earth history. And we're literally just a couple of seconds before midnight on this clock, the development of humans. And therefore, how this life developed over time was very much hostage to the types of environments that were existing at those different periods. And I don't need to tell you again that volcanic activity and, of course, the sun and another series of important processes all played a role in shaping that environment over time. So you really want to understand the early biosphere and how it's developed. You really have to understand the environmental context in which that development occurred. And with that, we then begin to get some principles out of understanding how the environment, early environment was, to understand the earliest origins of life, and also to begin to make some statements as to what other planets might have been like. This is sort of the disk around the sun in which the planets actually formed. We begin to get more insights as to what some of those other planetary environments might have been like. And with that, we turn to Mars. And the interesting thing about Mars is that it has been more Earth-like. The environment of Mars has probably been more Earth-like than that of any other planet in our solar system. It's not just that it's our next-door neighbor, but also the fact that it's a rocky planet like the Earth. From what we have been able to tell, it shares a number of features of the Earth. And so if there's a chance for a second occurrence of life anywhere in the solar system, Mars is really the leading candidate. So that's our particular interest. There's a lot of similarities. They both have a spin axis. It's about 22 degrees off the perpendicular with respect to the plane of the ecliptic with the solar system. And so therefore we have seasons on Mars, just like we do on the Earth. This is showing the southern hemisphere weather-wise, the northern hemisphere. And also these are highlands on the Earth and highlands on Mars, lowlands on the Earth, that's the ocean basins, and lowlands on Mars. So in a way, we have on the Earth what we call a crustal dichotomy. A dichotomy meaning two sort of characteristic elevations of the crust. The elevations associated with continents and the elevations associated with the ocean basins. Curiously, Mars has the same thing. It has the southern highlands and the northern lowlands, which we can explore in the next few slides. But the key point here, a lot of similarities. A tilt axis that gives you summers and winters in both planets. Sunlight, of course, bathing the surface, and a geography that has some interesting similarities. So here now is the Earth with the continents and those big ocean basins with all that volcanic activity. Here is Mars now with the southern highlands. This is a Mercator projection, and the northern lowlands here shown in blue. So the blue colors This is a huge meteor impact that probably hit about 4.3 billion years ago, creating this big basin down here. But the other interesting thing is I told you about all this volcanic activity that dominates really the Earth when you strip away the oceans. These are huge volcanic centers on Mars. And so like Earth, Mars has these very large volcanic systems that really occupy a lot of the geography, and there's a lot of lava flows in here as well. And so in many ways, Mars might be a snapshot of what the Earth looked like 4 billion years ago or 4.3 billion years ago. And in fact, because Mars is a smaller planet, that may well be the case. Mars's crust may not have developed nearly as much as the Earth's crust did, simply because its heat engine slowed down more quickly by virtue of the fact that Mars is a smaller planet. So in many ways, Mars represents a snapshot of certain things about the Earth that might have existed more than 4 billion years ago, which accounts for part of our interest in Mars. As we look again a little bit more closely, again we see the major volcanoes of Tharsis, Olympus Mons. By the way, that volcano, the base of that volcano, has the same area as the state of Washington. So this is an enormous volcano, the largest one in the solar system that we're aware of. And the key point is that volcanism and these impacts, these very large impacts, have really sculptured the Martian crust, and really they dominated the early environment. Well, guess what? We heard that before. Volcanism dominating the Earth's early environment, having a lot to do with geography at that time. And so we're beginning to see these similarities now between Mars and the Earth, and the key common denominator is volcanism. Okay, and then of course what gets interesting on Mars is when you look closer, you see these enormous stream channels that flowed across the surface. Some of them are erupting, water erupting from the subsurface and flowing out towards those northern lowlands. And given the inventory of how much water it would have taken to create these features, there could have been a northern ocean on Mars, sort of shown by this artist representation here. And that would be the case if the amount of water that was required to sculpture these channels actually did occur, in which there's a lot of evidence. In fact, the next slide shows some of our more recent orbiters that have excellent cameras that can really map the surface of Mars in great detail. They have found all these little red dots here, which actually are crater lakes. These are lakes that formed in these craters sometime after the craters were formed. They're called open basin lakes, which means they had outlets that allowed the water to flow into the northern lowlands. But look at the density of these things. And also these little blue squigglies. Each one of those little squiggly is a stream channel system with a lot of drainage coming together, small channels to bigger still channels. And every one of these little blue squiggles represents one of these features. The density of these watery features overlaps the density of features that we see on the Earth. It's now because of just imagery, this imagery is less than 5 years old. The imagery now indicates conclusively that it precipitated on Mars. Now whether that precipitation was just snow or was also snow and rain is to be determined. But this is what I mean when I say that Mars' environment was more Earth-like than that of any other environment we've been able to document. The only place where we don't see the density of these things where we would expect to is, guess what, where the volcanic center is. Mars continues to be active volcanically even today, and the volcanism in this area literally covered over these ancient channels and lake beds. So again, a lot of activity of water on Mars, activity that we wouldn't have dreamed of just a few short years ago. So the early Martian environment was much more Earth-like than that of any other solar system planet. It might have even had an ocean analogous to the oceans of the Earth. And in part, volcanic activity, putting gases into the atmosphere that would have helped to warm the planet at that time. It could be maybe that the volcanic activity being more active back then could have given more CO2 to the atmosphere to cause more warming to allow that liquid water to be more stable at the surface. And so we decided, oh, this is just too exciting to look from orbit. We got to go to the surface and look more closely. And of course we did that with the Mars rovers. Basically little field geologists with the wheels, giving them the mobility, the cameras, the visual capability to look for the interesting targets, and then an arm that both grinds into rocks and does analyses to tell us what these rocks are made out of. So we set one of these down. This is Opportunity and Spirit, but this shows some of the other places where we've visited the surface of Mars. So we're beginning to get now more of an idea of what the landscape looks like and what the history that's recorded in that landscape just might be. So I'm just going to show this one example just to make the point with the connection to Lassen, where Spirit went down, and it's in a place where a large stream channel filled up one of these crater lakes. This one's called Gusev Crater, and then the water overflowed and went down into the northern lowlands. And just for good measure, we got a nice big volcano thrown in there nearby in Apollinaris Patera. So we really hope to find some nice lake sediments here and really find evidence that there was water present. Took us a little while. This is now a National Geographic artist getting all excited about the mission just before it launched and doing this beautiful painting of what that lake might have looked like with Apollinaris Patera blowing off in the background there. So all in all, a very interesting place to go look for the water story on Mars. And here's where we landed. We land out in the huge lava plains, just lava, basalt flows everywhere. And we decided that what we had to do was to drive to these hills, and that's our little traverse here. And because this looked like, these hills looked like they were older features poking up above the margin of this lava flow. And so we went over to these hills to look for evidence of that ancient lake that we must have been there at some time in the past. And here's a little intrepid spirit driving up into the hills there. These hills were named after the astronauts of the Columbia shuttle, and Husband was Jim Husband, one of the 7 astronauts. Anyway, Spirit, this is of course an artist friend. We've plopped a model of the Spirit on top of the landscape here because obviously Spirit couldn't take a picture of itself, but that's pretty much what it would have looked like. The key thing is that when we were up on Husband Hill, we looked into this very interesting place called Inner Basin, and in particular this feature called Home Plate. And it was just so distinctive that we thought we really should go down and explore it. And when we did, this is this thing, it's sort of ratty looking, but it's about 90 meters across. What would that be? About 270 feet or so, and about just 6 feet high. But it's totally littered with lava rock, and it has a whole bunch of interesting features also. Some of these basaltic rocks are filled with bubbles, indicating when it erupted, it was just frothing with water. There's a lot of water in this lava, sort of like a lot of what you see when you go to Hawaii and you see the lava fountains and so forth. But the exciting thing is that we found salts rich in sulfates, both iron and magnesium salts, literally all around this thing. And when we dug into some of the deposits around the margin also, we found pure silica, very reminiscent of the type of siliceous silica that you see if you go to Yellowstone Park or to Lassen Park, where the hot water has come up, it's evaporated and left just pure silica laying around as a very whitish type deposit. Now this is very exciting to us because if you go to Yellowstone or Lassen and you find silica, it has a lot of textures of microbial organisms in there that were living there, and then they sort of got silicified, or there were molds made of themselves. And so we were very excited. This not only indicated then that we had volcanic activity, but that we had water, which was bringing up sulfur and bringing up sulfur gases, and it was reacting with the rock and forming these silica deposits. So not only now do we have evidence of volcanism here, but with water associated with it in the kind of environment which in a place like Yellowstone or at Lassen provides a source of near-surface water, gives you chemicals in the water that could provide sources of energy for life, mineral deposits that could preserve any evidence of life if it's there, and of course nutrients coming up in the water so that the cells can be built, and a whole range of conditions that could sustain a variety of organisms if those organisms were there. And indeed now we have found evidence of these deposits on Mars. So in this little valley here, in Gusev Crater on Mars, we see all the attributes that we see if we go to a big hot spring in Lassen or in Yellowstone National Park. So this, of course, is the source of our excitement for learning more now about environments in Lassen as a way to learn how we would interpret just the mineral remains of what that environment might have been like at some time in the past. And so with Mars then, we get this impression that billions of years ago, and this is sort of from billions of years ago up to today, sort of like a time march here, there was water, this blue sort of representing water in near-surface environments, but over time, perhaps as the volcanism died away, the surface environment got very cold and it got very dry. So if you want to see evidence of life on Mars, you look for evidence of past life in some of these really ancient environments that might be preserved in rocks, although now we have to learn how to analyze these rocks to look for that evidence, or you have to go about a mile into the subsurface where the pressure and the temperature are high enough that you could have liquid water. And of course, there's a lot of excitement about the potential for such a place being there today on Mars, and of course, that would be a potential human resource if we ever decided to establish settlements on Mars. In any case, this all sets the context then for how Lassen and what we do up there could give us more ideas about how we would do future exploration at Mars. Reminding again then, going to go to Lassen and try to seek out those environments that would be the best for microbial life forms, we have to follow these rules of picking out places where we have the water present, the energy available in some form, and all the nutrients available as well. And this is something that the students have labored to do in the field work and to follow up in the work they did in the lab and after that. Lassen, again, is just a wonderful place, as you all know much better than I, having just living here next to it, but it has this whole variety of different types of volcanoes. So it's really a nice template of different types of volcanoes that perhaps have a variety of these hydrothermal environments that could support life. So it's just a wonderful natural field laboratory that brings together the volcanic activity with the gases that are important for life potentially, the kinds of rocks that give nutrients, and of course the water. And again, the question, where in the park would we find things that would be most informative to us if we try to study the early Earth or study Mars? The field site, which you'll hear about, is right as you drive into the entrance of the park, and that is where the visitor station is, and where that road first finds its way up into the high country there. This is the remnants of a large volcano called Mount Tehama, and they'll tell you a lot more about the work that they've done in there to understand a little bit about the geology, the water, and how that might be relevant to life. And so basically Tehama and the water that comes in as snow or comes out as springs flows down through that valley, goes past a very interesting feature called sulfur works, and the students will tell you a bit more about that. And to really, again, try to understand the nature of these environments and how they might relate to the effort to reconstruct what an environment on the early Earth might have been like, and because of the similarities between Earth and early Mars, where we might look for evidence of life on Mars. And there's even insights then into our own futures in the sense of how we can understand the role of volcanism and microbes and how that might shape the future environment on the Earth, and how it might inform us as to where resources would be located in places where we might tend to visit in the future. So there's spin-offs not only for understanding our origins and whether we're alone in our solar system, but also to inform us about the resources that would be available for human exploration in the future. And with that, I'd like to hand it to the students, but I'd first like to thank you very much for all the support you've given in all the ways that only parents can imagine in making today possible. Thank you.
There may be some questions at this point, and I know there's a question and answer session at the beginning, but maybe it might be a little bit more relevant if you have any questions for Dr. Desmarais right now. Just take a short little, maybe 5 minutes or so to answer any questions that you might have relating to what he just talked about. Then we'll talk about the students who will come up here in a little bit. So are there any questions? Yeah.
Are the rovers still working, and how far have they traveled?
Okay, that's an interesting hit. One of the Spirit opportunity we haven't heard from it now for about 1.5 years, 2 years. So that one, unfortunately, its mission is over. Opportunity has survived in winter very successfully, making a bunch of measurements. In fact, I was on mission operations last week, and we're now coming into the spring season from where it's located, and we hope by early June to start driving again. We're exploring the margin of this huge crater called Endeavour Crater, that's brought up rocks from deep below that we've never seen before. In all of the 30 kilometers, that's 20 miles this rover has driven. We promised the world we would drive 0.6 kilometers. 0.6 kilometers, we have driven 30. We are in 3rd place in terms of records driven by vehicles on other planets. The Russians are in 1st place, Soviets I should say, in 1st place because their Lunokhod rover that was driving around back in, believe it or not, the early 70s. In 2nd place is the Apollo 17 astronaut buggy that drove around collecting samples back in 1972, I think it was. And Opportunity is now in 3rd place. And if we can keep this little rover going for another year or 2, we'll certainly get into 2nd place, and who knows. So they're still going. It's pretty amazing. Yes.
Just another little point. Can you talk about that the U.S. has been the only nation that's successfully landed on Mars? So that's the distinction between roving around on Mars versus roving around on the moon.
Oh yeah, well the U.S. is the only country that has successfully landed a payload on Mars that's functional. A lot of countries have landed payloads, and they're on Mars, but they weren't functional upon arrival. We call that litho-braking. It's not a good way to land a spacecraft. So yes, those little dots I showed you are all from our NASA missions, and so yeah, it's a lot harder. And in fact, keep us in mind on August 5th at about 11:50 p.m., because that's when Curiosity rover is scheduled to land on Mars using a powered descent thing called the Sky Crane. And if I had time, I'd love to show you an animation of that. But it's very dangerous and hard to land on another planet like Mars, because you could have just literally bad weather that day. So we think we've got all the I's dotted and the T's crossed from the engineering point of view, but late in the evening, August 5th, will be our 10 minutes of terror as we do clearly the most dangerous part of that mission. And the next morning when you wake up, August 6th, you'll know the outcome of that. Hopefully we'll have a picture for you. So, yeah.
How are they powered?
These two little rovers that I talked about, Spirit and Opportunity, are solar powered. So we figured one of the reasons the mission would end after a few months is that the solar panels would get dusty. We never counted on the wind, which blows the dust off the panels periodically. Much more dependably so for Opportunity than for Spirit, which is probably one of the reasons that Spirit got into trouble. It went into a winter with all very dusty solar panels. The Curiosity rover is nuclear powered. It's got an RTG. It's nothing like the big power stations that you read about in the news. No moving parts, but it sits there, generates heat, and that creates electricity, which it can operate on. So that will not have a lot of limitations that these smaller rovers did, and we certainly look forward to having that advantage. But you really can't get into that kind of a power system until you scale up a bit. The little rovers, Spirit and Opportunity, are about the size of riding lawnmowers, and Curiosity is about the size of a Jeep. So it's a bigger vehicle. Yeah.
Have they found any evidence of past life on Mars?
No. There have been claims of evidence of past life on Mars, but not yet. I mean, the one claimed in 1996 was it was evidence of a meteorite. But a lot of people have studied that since then. And what's interesting about that is that it's evidence of chemical processes and things going on with water in the meteorite that gives some very interesting insights about early Mars, and maybe what water was doing is it was interacting with the rocks that might be relevant to, leading to life. But I think the consensus now is that it's not evidence of life itself. A lot of people believe that the definitive evidence is going to require bringing samples back to the Earth and looking in our own laboratories. I can tell you, it's really hard, even in rocks on the Earth that are 3 billion years old, to really be definitive that you've got an example of a fossil. And so they feel that you're going to need to have that comparable capability in Earth-based laboratories to be able to answer that question. We hope to be able to do that return in the 2020 decade, but we all know the economic situation and priorities of the country, and we'll just have to go as it's deemed appropriate to do that. Yes?
How will you know you found life?
Well, some people are so bold as to say they'll know it when they see it. We don't make that claim. I think, I could list for you the various types of fossil evidence that we have, ranging from a morphology that you see like a shell or a bone or something like that. But as I said, most of the early history of the Earth is single-cell life, so we don't expect to be finding shells and bones on Mars. So we would probably some of these organisms make characteristic colonies, which we call stromatolites, which is sort of like a miniature reef made out of microbial biofilms. And that actually is the most common fossil life on the Earth, because it goes back billions of years. Some of these are very characteristic morphologies. We are now, even with our rovers today, able to observe rocks at a scale where we would see those features if they were there. So that would be a very persuasive line of evidence. Probably the most persuasive is at the chemical level. You look for distributions of chemical compounds that just cannot be explained by non-biological processes. And I say we have a lot of observations of non-biological organic matter. We see it in meteorites. There's one that's a meteorite that landed near Coloma that you may have heard about a week and a half ago, is of the type of meteorite that's several % organic matter in it. And people have analyzed meteorites like that. They found all kinds of really interesting stuff, but they can clearly say that that's not from life compared to what we see in old rocks, actually. So a chemical analysis would probably be the most definitive thing. But the answer to your question is a little bit iterative. We have to look and see, change our strategy and adapt. And that's why this Lassen study is so important. It sort of gives us a sense about how to do that. So, yeah.
So if we think that Mars is similar to what Earth was 4 billion years ago, and we're looking for life on Mars prior to this, are you thinking that it's a cycle that, like Earth did not host life until 3 billion years ago and now hosts a lot, that we think that there was life and then disappearance and then life comes back again?
Okay, well,
Could you restate the question?
okay, I guess the question was, we're emphasizing early Earth, early Mars. Is the idea that life could have started on Mars earlier than Earth, or?
Right, because we're saying Mars is like Earth 4 billion years ago when Earth didn't have any life on it yet. Are we saying that Mars is currently, I mean, why would we look for life on Mars when we think
Okay.
it's at a point where before Earth had life?
Okay, thank you for saying that, because it allows me to mention something I should have mentioned about Mars that's a huge advantage over the early Earth. All that geologic activity I talked about on the Earth, it's made the continents, it makes the environment habitable today. That churning, that heat, and all that's happened to the crust has destroyed the Earth's record prior to 3.9 billion years ago. We don't have a record anymore. We know, looking at Mars, the record's there. Okay? Now, if anybody walks up to you in the street and tells you they know how long it took for life to begin, don't believe them. I mean, we don't know the answer to that question, but it could be very short. It could be 1 million years. So life could go back 4.3, 4.4 billion years ago, for all we know. But we can't answer that question on the Earth. The record's been destroyed. The attraction of Mars is that record is there. Okay, and it's a record that has a lot of water involved. So that's probably the key perspective there. And thanks for that, because that allowed me to mention another advantage that we have with Mars. So, and we can answer questions later on after this presentation. It's fine.
Thank you very much.
Sure, thanks.
In 2008, when this program, this partnership kind of started between Red Bluff High School, and in its current form, between Red Bluff High School and NASA Ames and Lassen Volcanic National Park. Really, the students that we had here at Red Bluff were basically conducting tests that were kind of outlined for us. The students here had a great opportunity. They were able to go up to the park, do field research, deal with all the obstacles that faces, dealing with weather constraints, just meters that might break, things like that. And so it was a real great experience for the students to go up there and do that. Some of the data that was discovered at that time, basically what we were trying to do was cycle water amounts. We were trying to see the pH levels of water. We were trying to see the conductivity levels of water in these specific sites throughout the course of a year. And once we found that, basically it opened up a whole nother set of questions. And the cool thing that these students have been exposed to over the last couple of years is really the application of the scientific method out in the field. Here, as a teacher at Red Bluff, as a teacher at any school, one of the things that you try to do in science is you try to expose these students to the scientific method. The students get that day one of really any science class, but they get it in a classroom setting. And what the students here in this program have been able to do is take that scientific method and apply it to the field. And what they've been doing over the last couple of years is actually conducting research, not just doing what they've been told, but also basically coming up with their own hypothesis, coming up with their own conclusions, coming up with their own analysis. They've been doing some amazing stuff that really is college level, and these students are going to
Could you address what those were?
I'm going to let them do that. Okay, I'm going to let them kind of talk about exactly what they've done over the last couple of years. But what I want to do is just kind of set the stage for this and tell you that what they're doing right now has prepared them in a lot of different ways for the obstacles that they're going to see once they get to college. So they've really been given an opportunity to get some real valuable experience here in high school. And really the culmination of that is right now. Because right now you're going to see some students come up here who are presenting to you their findings, and some of them might be a little bit uncomfortable in doing this. Okay? But I know that they're going to do a great job. I'm very proud of everything that they've done in the course of this year. I know all of us are. And so with that being said, you guys are up. Make sure you introduce yourself.
Alright, so we're starting with introductions. Hi, I'm Cassie Fuchs, and I'm a senior.
I'm Garrett Spangler, I'm a senior. I'm Austin Chase, and I'm a senior as well.
My name is Renee Rodriguez, and I'm a senior.
I'm Luke Kitchell, I'm a senior.
Hi, I'm Olivia Henderson, and I'm a junior.
Hi, I'm Meredith Lord, and I'm a junior.
I'm Jessica Dawson, and I'm a junior.
Hi, I'm Justin Lebeau Penadar, and I'm a junior.
So I'd like to thank you all for coming. We're finished with this. We broke it down into what we're going to be talking about. So we have our intro, which kind of goes over like volcanism, hydrological cycle, and all the stuff that we learned like first semester to be able to set up for our experiments. Then our field observations, which led to our experiments. And then we have two groups. So the water biology group is going to explain theirs, and then the water geology group is going to explain theirs, and then we'll come back to the big picture.
Okay, so I don't have that.
Okay. So what is astrobiology? Astrobiology is the investigation of origins, distributions, and future of life in the universe. The key aspect of astrobiology is to search for characteristics of the full diversity of habitable environments like Dave Duber told us about, both on Earth and other planets. Volcanic activity and its environments with water are key aspects of ancient habitable environments on Earth, which is what you just went over with all the volcanoes and learning about how the water was there before. The whole reason we link with Lassen is because Lassen Volcanic National Park provides field sites where volcanic processes interact with the water and also host microbial So the Lassen Astrobiology Intern Program, which is here, it explores volcanism, water, life, and interacts to sustain microbial ecosystems. So with that, Eric's going to explain what we do.
So basically with this program, there are two main objectives that we have to it. So the first one, basically just to expose us as students to the kind of NASA way of life and to allow us to get hands-on experience with experts in their field. And then the other one is kind of how what Cassie and what Dave touched on is that we're actually contributing our findings to the Mars cause. And so, like Dave put it probably a lot better than I will, but basically what we did is that going up to Lassen, what we did was able to, that we went up and observed and analyzed the relationship between water, the geology of the area, and the life of the area. And then so, by looking at those relationships and being able to discern the key points in those, we were able to take that information and that macro ecosystem and then look at the microscopic ecosystem at play at Lassen. And so we can see how the microbes interact with the various minerals that the geology gives off and how the water affects those minerals and the microbes. And so they're taking that information, we can kind of go backwards and go to Mars and see how the different mineralogy and stuff like that on Mars, and then create a story of a possible macro ecosystem and stuff like that. So
essentially what we're doing is we're taking volcanism, water, and life and looking at the synergy of it and how it works together.
In our specific field site, there's a few things that we focus on. With volcanism and the hydrological cycle together, it creates a habitable environment in Lassen that is very unique and fun to look at. So
this right here is a picture of sulfur.
Yeah, big mud ponds. Volcanism in Lassen is a unique story. The main mountain that was there before was Mount Tehama, but is no longer there right now. It was an andesitic composite volcano. The remnants of it is still present in sulfur works because it has the same source of gas that is said to have corroded the volcano, but also water erosion led to the destroying of the ancient volcano. The water in sulfur works is very acidic because of the volcanic compounds that are present underneath the earth that we don't really see, but we smell for sure.
So the hydrologic cycle is in the Sulphur Creek watershed obtains water from precipitation, snow, springs, and rich lakes. The water eventually ends up all the way down in the Sacramento Valley. Other rich lakes, it's really rocky with full of vegetation, and it's fed by three streams occurring in rich lakes then feeds into the sulfur works, and the sulfur works has a distinct sulfur smell.
she said she just went through the process. It starts up here, after precipitates and rain down, flowing at the top and working its way down the mountain.
Okay, what makes a habitable environment? There are a few key ingredients, such as the chemical requirements that microbes need, the energy, some favorable conditions, and the water. The chemical ingredients that the microbes use are minerals that come from weathered rocks. Some energy that they use from light from the sun, or chemical energy. Favorable conditions are the correct pH and temperature for the water, and those are caused by volcanism and the hydrothermal vents. And the water is provided to the microbes by through both snowmelt and hot steam that comes from the volcanic magma.
Alright, so kind of our observation. Geology really looked at Ames lakes, and then biology we want to focus on sulfur work. So for this program, we split up into two main groups. For biology, it was me.
It was me as well.
And then
And I was in the biology group as well.
okay, and then the geology group,
Garrett, Luke, Renisha, Meredith.
Alright, so basically, when we went up to Ridge Lakes and Sulphur Lakes, we observed a very key pattern with the Modiel geology that if you look at the geology, even just like on a very clear visual level, you can see that the different rocks are altered differently. And so that sounds kind of redundant, but I mean, like what I mean is that the being exposed to the different environments such as Ridge Lakes and so forth, these rocks were exposed to different levels of acidity in the water, and so that they became weathered is something I'm getting a little ahead of myself. But we were able, like color-wise, we were able to observe that like the rocks and sulfur works were a lot lighter and a lot more weathered than the ones at Ridge Lakes, who seemed a little bit more the usual kind of like a, what's a healthy rock, but like more like a base rock structure. And then so basically what we wanted to do in the geology group is to recreate that kind of weathering in a rock environment.
Now, as the biology group, we mostly focus at sulfur works, specifically the upper side. Now, sulfur works, as Dr. Day said, is a very specific place where you can see volcanic activity. As you guys have probably seen, since most of you have probably been there, you can see a lot of gas coming up, which actually is volcanic activity. Now, our main idea when we were hiking there was volcanism on Earth versus volcanism on Mars. So we already knew on our hikes that the water in there was acidic from the oxidation of sulfide. The sulfide comes from the magma down in the mantle. Now the sulfide was being oxidized into sulfuric acid. Now on one of our hikes we had specifically seen some purple bacteria at the bottom of the sulfur works. So we thought, couldn't these bacteria too be using sulfide oxidation as a nutrient? So that is what we based our hypothesis and experiment on, to set up an environment similar to that to see if they weren't using sulfide oxidation.
Okay, so our actual hypothesis for the water biology group was that we saw these purple bacteria, and we wondered if they were doing anoxygenic photosynthesis using the sulfur present in the hydrothermal vent. So we hypothesized that the purple bacteria were actually performing anoxygenic photosynthesis. Okay, so we set up our lab, and we set up our control group, and we had 3 different groups, but the main thing was that we wanted to find out if they were doing anoxygenic photosynthesis.
And this equation here, we actually had to figure out ourselves. Maybe like kind of set us up and help us to where we had to get to, but we had to figure out all this chemical equation and balance it out, which was fun.
One of the reasons why we came upon this hypothesis was that this equation yields 2 hydrogen ions every time it happens, and hydrogen ions produce acidity, and so the hydrothermal vent was very acidic, and so that led us to believe that the microbes in the vent were actually undergoing this process.
Yes. We used a series of test tubes, some buckets, some syringes, and some 0.2 micron filters to collect the samples. And as Austin mentioned, we wanted 3 types of samples. One that was pure water, one that had some bacteria, and one that had a lot of bacteria. To collect each sample, well, to start off with the pure water, we collected some of the solution into the syringe and then filtered it using the filters. For the soma bacteria, we collected a mixture of both bacteria and some of the water from the solution. And for the Elata bacteria sample, we collected from a highly concentrated area of bacteria. And we used a pH meter as well to calculate or measure the temperature of the solution as well as the level of acidity.
Our results. We took those readings for a total of 552 hours, which is a little over 3 weeks. Now, with our 3 samples, we had the Elata, which definitely had a high amount of our purple bacteria that we thought would create the water, transform the water into more acidity over a period of time. Now, as our results show that in fact the Elata sample did become more acidic over time, supporting our hypothesis. Now, the graph that I will show you, you can specifically see this at time 10, which is the 10th time that we took the measurement, which is about 240 hours. At the pure water sample, which had nothing in it because we wanted to make sure that it was not an outside source, that the water could be doing itself. It had a slight variation, but it did not have enough to discredit our hypothesis that the bacteria were in fact doing it. Some microbes became slightly acidic over time, which supported our hypothesis because we thought that maybe there would only be a small amount of our purple bacteria in there, so in fact the water would only become slightly more acidic. Now, at the time I was talking about, which is right about there, you can see the immense decline. Now those two, we took 2 samples of the Elata and 2 samples of the pure water and 2 samples of the some microbes. The 2 drastic changes are from the Elata, which this is the pH, so as you can see, they became more acidic. And these are our duration. Those cluster of lines, as you can see, are the pure water and the some microbes, which did not have a very big differentiation from the beginning.
So basically for our group, we took samples of andesite rock from the field and both altered and unaltered andesite rock. We wanted to simulate in the lab what we observed in the field. So we had 2 control samples and 2 field samples. We crushed the samples and placed them in solution and also in the environment. So then after a period of time, we sent the water in for analysis and then we confirmed for that. So our hypothesis is we believe that we can simulate in the lab, of course, what we observed in the field, and the entire purpose was to show the weathering of rocks in the hydrologic system. And the sulfuric acid in the lab should react similarly to the unaltered rock as the sulfur goes in.
There's some methods that we had to use from just the visual observations that we made and the actual collecting of the data. We collected rocks and water from the Lassen site as well as just water from pure water. We used the pH meter as well and the conductivity meter. We used syringes to collect, and I collected little bottles full of the water up there. And it was just an overall collection of fun stuff.
Right, and so the geology group, we basically kind of did the same thing, but we had a little bit different spin on it. So with our lab measurements and observations, we had to basically do the same thing as the biology group, and so we had 4 measurements, and so we had temperature and pH, which the pH meter gives a temperature reading as well, and so with one machine we were able to take those 2, and with conductivity, which basically is the measurement of how well electric current will be able to flow through that medium. We took a conductivity meter, that makes sense, and then microscopic images of microbes. Basically what we just did was from the biology group, they were able to take samples of the microbial life that we found in the field, and then just use microscopic images of that, and then we also use that to kind of discern what kind of minerals that would be popping up in the our water samples as well. And then for specifically the rock samples, we used a machine called a Terra, which basically what it does is that what we had to do was take our rock samples they found in the field and grind it up with a mortar and pestle. And then we sifted that powder to get a particular grain size. And once we got our ideal grain size, we then put it into the machine that basically fires X-rays and not done yet. Okay, so basically, Terra. So we put those grains into the machine. It fires X-rays as it, and then and every single mineral has a different structure. And so when you fire that X-ray at it, it will reflect a particular way, depending on what mineral it is. And then you can take that reading and then put it up against a big database that NASA has of various minerals they've taken measurements of in the past. And so we were able to discern what kind of minerals made up our rock samples in the field.
And before we go on, the conductivity meter that we keep talking about, conductivity measures like how much conduits are dissolved in a certain liquid. And so we're testing to see like if there's a high amount of conduits or a low. And so that's what that meter does, just to kind of explain that, to be thrown that word out.
Okay, so this is a basic bar graph that represents the elemental analyses we took of our samples. The y-axis here represents the amount of each element we found in our samples in micrograms per liter, and the x-axis represents the elements we analyzed for. We analyze each group for aluminum, calcium, iron, lithium, magnesium, manganese, potassium, silica, and sodium. And we analyze 6 different samples. We analyzed pure water, pure sulfuric acid, then we did a control group of andesite rock in this distilled water and in sulfuric acid. And then there are field samples, which are unaltered rock from the upper side, which is Ridge Lakes, and altered, which is from the upper side at Sulphur Works. The general trend was that our field samples held more of each element than the control group did.
All right, so before we go into the discussion, just to kind of give you an analogy of what our NASA Astrobiology Internship Program does is we kind of have a puzzle, and you guys have all done puzzles, so you always look for the corner pieces or the piece that you can eliminate and know which way the puzzle goes. And really the puzzle can't be completed until we go to Mars and actually get there. And so it can't be completed until we go to Mars, but the goal is to get as many pieces set up here, and that's what we do. We just get pieces ready for when we go to Mars.
Can you go back to the last slide? As if you're talking about. All right. Taking the results into consideration, our lab certainly did parallel what we've observed within the field. However, the concentrations were off. The Sulphur Works upper site had noticeably more elemental displacement than the results from our lab did. We believe there are 2 real reasons for this. First, our experiment was over the course of 1 month. But at Lassen Volcanic National Park, of course, these rocks have been eroded for many, many years. The other reason our lab results show the lower elemental concentration is because of microbes. At Lassen Volcanic National Park, there are a lot more microbes than there were in our lab. Typically, the more microbes there are, the more acidic the water is. Therefore, more microbes means more elemental displacement. As you can see with the results. And so the lab is andesite, distilled water, and andesite sulfuric acid solution, the top ones. Then the bottom 2, those are out in the field. Anyways, there's a cycle here. The microbes live off of these displaced minerals. The area is essentially made habitable because of the minerals. But what is the significance of learning about these habitable environments? Well, we are really just planning for the future. We are expanding the NASA database. These results can be helpful, as in the future, it may facilitate the search for life. Right now, these observations are especially significant because Lassen Volcanic National Park has some very similar qualities that Mars has. On Mars, there are volcanoes, and of course there's also water, as Dr. Dave Rice covered a minute ago, sorry. Because of this, many have concluded that life could have existed here. If life exists in such conditions that we have seen at Lassen Volcanic National Park, life definitely could have been present on Mars at some point in time. This is what we've done at Lassen. I got 4 hours to get left. Try to bear with me. Alright. This is what we've done at Lassen to search for life that may have existed on Mars. NASA can take rock samples and analyze them just as we have. The possibilities of where this research and similar observations will take us is truly uncertain. We are confident that it will push us in the right direction, towards better understanding our world and our universe. Some might say that the sky is the limit, but with NASA, the sky is really our playground.
Before we get to our last slide, does anyone have any questions about what we did in our experiments?
I just want to know if we can get access to some of these pictures that you guys.
I have them all. Have them, and then also, I don't know, Sandy, can you get them off the site, or awesome?
You
Okay,
got
so,
some great pictures.
well, yeah, so,
All your
I
hard
don't know.
work.
They're on our website.
We have a lot of pictures.
And so I will tell you what the our website is.
Yeah, I've done the website, but I haven't been in the past few weeks or whatever, so maybe I'm on the wrong page.
I'll write it down for you and give it to
Thank
you.
you very much.
You're welcome.
Yeah, you're talking about different microbes and how we consider, I guess, the sulfur works kind of a hostile environment. So if these are extremophobes, is that why you're focusing so heavily on the sulfur works, because the Mars environment would also have been relatively hostile?
Yeah, it could be, it really depends on the area, because it's so cold there that they would have it like the opposite extremophiles, but it's the same idea of them using like a different type of photosynthesis than what we're used to.
What did you guys think about Lassen as a field site? Do you feel like going to the park was beneficial? You learned more than if someone's just mailed you?
Oh, definitely, yes. I mean, like, yeah, there's a whole different level of like learning that you get from learning in the classroom and then going out and doing it and actually to see where this would, and like where your knowledge that you obtain actually would apply. And so, I mean, like, using Lassen as a field site was really beneficial to making it work here. Like, awesome, I'm out here.
Yeah, well, I just setting aside the fact that we're conducting research with NASA scientists, just going up to the park and hiking up there, I mean, it's beautiful. And it's a great hike, and you get, I mean, we leave school early in the morning, we go hike all day and eat lunch up there, and enjoy ourselves.
So what you're saying,
yeah, I mean, have snowball fights, I mean, it doesn't matter, right? So, I mean, that's really enjoyable, and then you throw in the fact that we're with world-renowned scientists doing research and getting to apply classroom knowledge outside just the textbook. I mean, I definitely enjoyed Lassen National Park. But we're going to go through and just say, like, what the program's done for us, like each of us.
And then, all right, so we haven't told the juniors about this yet, so we'll go first, let you guys prep for a couple seconds.
So we've been in the program with seniors for 2 years, and they've been in it for 1 year. So I mean, just go through and say like what this program has done for us and like what we've taken kind of to heart with it. So Kathy.
So this program, I got to learn a lot. I got to use a lot of the science equipment that I will be using in my future. So for me, that was pretty exciting. Going and seeing NASA Ames personally was my favorite part. Just like being there and actually doing the analysis with them. Like it was just super exciting. So I just learned so much, and yeah, I like it.
And for me, along with, like I said, about working and getting a hands-on experience with NASA scientists, which is always awesome, that for me, that this experience has kind of made stuff in the classroom more real. And so, I mean, for like we get pounded with like the theory behind all of these like all of these ideas within the classroom, but then to actually see that applied and actually see that how it's proven in the field really establishes and like and solidifies that those ideas for me, and to see how that actually is applicable to our world. So that's how me for me.
Well, there's a couple things that the program has done for me. Like we applied at the end of our sophomore years to be in the program as juniors and seniors. And so, I mean, obviously the first thing that you see with this program, and it's not the most important, but this program reaps like huge benefits for college. for our applications. It makes us like really unique in an application because this is one of the best one of the only internships. And so, I mean, I really valued the program like and my self-interest for that, as in like made me unique in the college application. I'm sure it made all of us. But also, just kind of like going outside your comfort zone and doing things you're not used to. I mean, I didn't know like how to work a pH meter or to work on a conductivity meter. And I mean, like when you go outside the classroom and you're not in the day-to-day basis, like of just class, you kind of just get to be yourself and you get to do this awesome research. And I mean, I really enjoyed doing it for 2 years. I'll definitely be sad next year that I won't get to do this anymore.
Okay, so for me, there was again two things. One is just Lassen as a whole. Like Steve mentioned before, there was a summer internship program that I also got to be a part of, which was a great experience. And I think that I've made some good connections with Lassen as a park and also with a lot of the people there, and hope to pursue that later, maybe, we'll hope. And then also to see all these inspirational people that like have pursued like just a subject in science and have come out on the good end of the spectrum, and I think that is a good way to be a role model and show us. And I think it was great to meet all of the people that worked really hard at NASA that maybe we might be someday. And that's like the goal for us to be. So I think that's what I'm getting from this program.
Well, the program really does take a lot of time, but I want to say I think it's very well worth it. My favorite part of mine is probably just being out in the field, hiking. But also, I mean, I really do feel like I've learned a lot. I've always been curious about the world, about what else is out there, what's in the future for America, for the world in general. So I really enjoyed just getting to know more, and of course working alongside NASA scientists, and of course Steve Zachary. And I mean, we really do learn a lot.
Okay. So personally for me, I'm a very big nature lover, so getting the opportunity to go up to the mountain all the time, that has been a big treat for me. And it's also provided a lot of real work experience to kind of usher in the futures that we're going to be, the careers that we're going to be getting into very soon. So kind of a preliminary program, if you will. So I value that.
For me, ever since I was little, I remember playing with my little solar system game, playing with my chemistry set, or like seeing the new scientists on the TV and stuff and going, I want to do that. Now with this program, I've always known I wanted to be a scientist, but it's actually brought being a scientist to me sooner than later. I've gotten to work with great doctors like Dr. Dave and Nikki and other scientists like Mike and even Mr. Michael. So learning how to use a pH meter, a conductivity meter, and what it is to take samples in the field has just brought my dream of wanting to work with science just come true.
For me, I love science. It's like one of my favorite classes in school, and like the entire experience of just doing this was really fun. Getting to go hike and go to the Ames place was really fun. Yeah, so basically the overall experience is just great.
And for me, I've also been, I've had an earth science class this year as well as a biology class. So having this experience through this program has helped me utilize some of those skills I learned in earth science and connect more of the ideas. So it's actually broadened my mind more than I thought it would at the beginning of the year.
Awesome. All right. With that, we have some people that we have to thank because they just made this program possible and they're amazing. So as we call you, if you could please come up, starting with Sandy.
Alright, so just to say something about each of the people, Sandy does like all of, just kind of like the journalist mom kind of for the program. And I mean, like, I definitely look at her like she's always reminding us when we need to do something. She's always there. I mean, like, if you want to chat with her, she's definitely like the NASA mom. And like, I just really appreciated getting to know Sandy over the last 2 years and all the hard work that you put into the program. And so, I mean, she doesn't exactly get the benefits that we do from the program, but she dedicates the same amount of time, if not more, than we do. So thank you, Sandy.
Thank you very much. What's up, Nikki? And Nikki was our microbiology She helped us so much. We learned so much from her. And she's just helped us along with our process this year and last year, just teaching us everything with like the synergy from the beginning of the microbials and how they interact with the water and everything. And while doing this, she also has, of course, she has to do her job at NASA. So being able to get back to us as fast as she did is just amazing and just always being there for us.
And then next we have Dr. Dave Marin. And I mean, obviously you guys have seen from his speech, he's just an extremely intelligent man. And I mean, you can ask him anything and he'll give you an answer, even if it doesn't have to do with NASA. And like, I've just enjoyed over the past 2 years, like not only being able to do research with somebody who just has such a profound effect on NASA's research, but just to be able to like talk with him about different things and I mean, pretty much anything. And he's a great guy and I really appreciate everything he's done for us in the last few years. So thanks, Dr. Dave.
And next up, Mike Kubo, which he was not here, but he was really amazing. I was in his water chemistry group last year, and one most important thing I learned from him was Excel. I know that program inside and out, and he has a great personality as well, like a part of just like teaching us so much. So I want to thank him, even though he's not here.
Very cool.
He's in Hawaii.
No, I thought.
Wait, he's in France, isn't he?
Yeah, somewhere cool.
He's in France on his honeymoon, so don't feel bad for him.
And okay, so this is Mr. Zachary.
Yeah. He was the park ranger that helped lead us through all the hikes, and he just has a plethora of information about the park as a whole and just in subsections. And I've learned a lot from him about what it takes to be a park ranger, and it's a lot more than a lot of people would imagine. So it's really impressive to see where he's come through with his life and how much he has helped us with understanding Lassen as a park.
Mr. Michael's going up here.
Alright, so Mr. Michael is a guy on campus. He always kept us on task, and he was just awesome at keeping us all organized and get us the place we need to go. And so, yeah, and even apart from being able to keep us being our leader we look up to and keeping us focused, that he also especially with us seniors, he's helped a lot in discovering and giving us advice on what we want to do for the rest of our lives, especially with college. And so I know that we've all had talks with Mr. Michael about college aspirations and such, and so I just want to thank you so much for all of it.
To add to that, when you're in high school and you meet your teachers, and a lot of kids, you don't think they have lives outside of school. And I mean, I think it's been really nice, when you get that opportunity to connect with a teacher and get to know them. I mean, nothing's really like that you can have at school, so it's been really nice. So thanks, Mr. Michael.
Because obviously, if it wasn't for you, we wouldn't be here because you're the one who picked us. And last but not least, Mr. Biltruth.
Alright, well unfortunately Bill Trude is not here today. It's actually his first year helping out with the program, but he really has made an impact. He drove us several times, and we're hoping he'll help out next year as well. He's also the Alpine coach, so he is a teacher. And yeah.
Bill Trude.
Awesome, so thank you guys very much for listening to our little spiel.
Thank you.
Oh, yes, sir.
Could you seniors tell us where you're going to college and what you're going to be doing?
I'll let you guys start first.
Go ahead.
I'm going to UNCW, which is University of North Carolina, Wilmington, and I'm majoring in criminology.
I'm planning on going to UC Santa Cruz. I'm not exactly sure of my major, but I'm thinking business. I've always been business oriented. I'm really looking forward to it.
All right.
In the fall, I'll be attending UCLA, and I'm on the pre-med route doing microbiology and psychology, and so that's what I'll be doing this year. But I might switch to something else.
I'm going to Butte Community College, with then transferring over, hopefully to Chico, to become a math teacher. That's my ultimate goal. So.
The last is a very awkward question for me because I'm undecided. And so basically, I'm not entirely sure where I want to go to school yet, but what I want to major in is I want to end up being a physics teacher. And so that's kind of my aspiration to take me. So, yeah, so there you go.
Thank you guys.
Any other questions really fast?
Of course.
No.
He always has a question.
It's related to the guys' topic.
Okay.
The doctors, when you guys communicate to the rovers, how do you do so? And what's your return time from the command to the response?
Okay, well, all the deep space communication goes through the Deep Space Network. There's a Goldstone dish, there's one in Spain and one in Australia. So no matter where the Earth's rotation is, we're always able to look at any target we want. So there's two modes of communication. We do uplink for the commands every day, and that's a relatively small packet, so we can go direct to the rover with that using X-band. And that's it's great because it's fast. As soon as it gets to the DSN, it's there basically. But it's expensive for the rover. It has to operate its dish to receive that signal from the Earth, and it's not a lot of data. It's enough for us to send up commands. The rover does its thing, and what we've learned over the first year or two was to, rather than send the data back to the same thing, which burns up a lot of that precious solar energy, we do a UHF band link up to an orbiter, Mars Odyssey, which was launched in 2001, and then later Mars Reconnaissance Orbiter. And so they do a UHF relay, and then they got all the power they need. They've got these big solar panels, and they send that back to the Deep Space Network. That has a latency of several hours, but we really don't care because we're sleeping at that point. And the next day we wake up and there's the data, and that's how it works. So we have to go up with X-band and come back to the satellite. Oh, and I gotta tell you this. You know, I talked about this heat engine, right? So we'd love to know how much the interior of Mars is still molten. If you've ever spun a raw egg and then spun a hard-boiled egg, you notice that the hard-boiled egg spins differently. We can use the X-band as a rangefinder. And what Opportunity's been doing over the winter time is making very precise distance measurements with the Earth to determine how it's swallowing as it rotates. And we've now gotten 4 months of observation and have a pretty good idea as to how much of the interior of Mars might be molten, which is obviously very important to the story I told you tonight. And so it just shows how people with the right ideas at the right time can just come up with some pretty amazing stuff. Okay.
Before you went, is there a way we can get a picture of all of you together?
We're not done yet.
Okay, we're not quite
Oh,
done.
okay, sorry.
A little bit more. I think Ranger Zachary and...
Oh, yes, that's right. We'd like to present each one of them in appreciation for their contribution to the park of NASA and to Bluff High School. And if we come up,
Yeah, I want to take just a few seconds to make a couple of comments just about the mechanics of the program. As Luke said, this program takes a lot of time. It spans the full academic year. We start with lectures to give them a lot of background information, and then we move into doing the field sampling at the last week, a lot of training, how to use the instrumentation. And then they start developing their research projects. And so in terms of the lecture material, some of this is college level lecture material. Some of the microbiology lectures I give, probably sophomores and juniors in college at the same level. So it's quite challenging. And they've risen to the task. It's also a huge time commitment. And so we want to honor that. And you can see that from the presentation they gave that they did a very excellent job. I was really pleased with what I saw. They really took ownership of the program. So again, we have some certificates, and we would like to honor them for their commitment and everything.
and Mr. Michael and we haven't added up the total amount of volunteer hours that they have contributed yet, but I'm sure it's hundreds of hours of time that they have put in for this project, above and beyond their normal school activities and all the other things that they do in high school.
That's something that we really can't stress enough. I mean, they're doing most of this stuff, or all of it, outside of school hours. pretty much every Monday when students get out at 1:20, they're working with me in a classroom until about 3 o'clock every single day. And they're not doing it for a grade, they're not doing it for credit or anything like that. They're doing it because they love what they're doing. And so it's been a very cool opportunity for them, but they have definitely returned that opportunity for production. They've done a great job.
So we'll start with the seniors. And first, I'd like to call up Austin Chase. Next, we have Cassie Brooks. I practiced. Next, we have Luke Kitchell. And next, we have Renesha Rodriguez. And I should show you what these. So next we have Garrett Spangler.
Juniors.
We have the juniors. Now we have Jessica Dawson. And next we have Olivia Henderson. And Justin Levoa Padar.
Justin is going to be in the summer program also. He's excited about it, and so Justin in the summer program.
And last but not least, we have Meredith Lord. So we have 3 other certificates to hand out. So why don't we go ahead and give the students another round of applause. This next one, as I mentioned, this is a huge time commitment for the students, but also it's a huge time commitment for the He has shown such dedication to the program over the last 4 years. And he's a very busy man in addition to advising this program, going on all the trips, supervising all the classroom lectures, all the classroom experiments that were done. He also coaches basketball and track, and we've also expanded the program from year to year to year, and he's hung in there, and he's been very patient with us as we've done that. And so we really want to thank you for your time. And another teacher who's been extremely helpful, Mr. Bill Treat, but he's unfortunately not here tonight, but he has assisted with driving. He's been out in the field with us a couple of times, and we really appreciated his contribution.
His enthusiasm is great.
And last but not least, Mr. Steve Zachary. Doing research with another national park, Yellowstone, for about 17 years. And I have to say, compared to my interactions with Yellowstone, which have been fantastic, it's a very large park, there's a lot of bureaucracy, sometimes it's a little difficult to get things done. It has been so wonderful to have Steve as a liaison. He has been excellent in facilitating this program. It would not exist without him. He's been an absolute pleasure to work with. His natural history knowledge of the park has added a lot, as we just talked about the microbiology and geology, he's adding a lot of content in terms of vegetation and other animal life and variety of things. So we appreciate everything that you do. Okay, well that concludes the certificate session. So now you'll see on your schedules that we do have about a few minutes set aside for further discussion. out there and we can direct them to the appropriate people. We can answer the students as well. So, you guys have anything else you want to chat about? Well,
I appreciate all of your support.
yes.
And it's just been a pleasure to have this program in Red Bluff and at Lassen Volcanic National Park. It's a real bonus for everyone. Thank you for your support.
So thank you to the parents. I think Sandy, we're all gathering now for dinner at, where's the restaurant again?
Casa Ramos?
Casa Ramos. So,
Anyone and everyone's welcome.
yes, everybody's welcome to join us. We've let them know we have hopefully about 30 to 40 people coming. I think we panicked them a little bit. They were overheaded over there, so we can have fun and be wonderful to join us.
Would somebody want to get a picture of you?
Oh, yeah, let's go to the streets. Thank you.
Go ahead, it doesn't matter.
Anybody else do camera? Send the pictures
very
to
hard.
Sandy, maybe I'll get them to Sandy.
Yeah,
But
I'll get you pictures.
I never take these.
Somebody's waiting.
Yeah.
Oh, I'm sorry. Oh, you're fine. We got you.
Is everybody, Sandy, what are you doing over here? You're supposed to be up there too. Sorry.
Well, it's the students.
Hi.
Go ahead, this doesn't matter. We're done.